Good morning, everyone, and very welcome to this seminar on mastering motor inverters, balancing efficiency, space, and costs. We will feature this on a heat pump reference design, and this seminar has been prepared jointly in cooperation between STMicroelectronics and Würth Elektronik. My name is Andreas Herder, and together with my colleagues, we will present you today this very interesting seminar. But before we jump into this, a few housekeeping notes. So all the participants will be muted in order to allow the speaker to be understood by everybody. And if you have any questions, please put them to the chat. We will answer them in the Q&A session at the end of this seminar. As a side note, very important for you to know, we will record this seminar, and so this will also happen. We have prepared this seminar in 6 chapters, divided by, let's say, we will start with the exploring of the application reference design. We will address the challenges which are coming with high voltage motor inverter designs. Also, we will address the right EMC strategies, how to ensure the compliance with the standards. On the front end side, we will be on the front end side. We will be taking a look on the active PFC solutions. And also we will take a deep look into how to optimize the passive components and the incurred design considerations to achieve the best strategic component selection. At the end, as I mentioned before, we will come to an interactive Q&A session where we will answer your questions. In the first chapter, we will take a look into the heat pump reference design. But before we do that, we will take a look into the overall application block diagram. Starting from the single phase or triple phase grid connection, we have as the main pillar the power stage, which can be realized in various different integration approaches. Either an intelligent power module or ST-SPIN32 or discrete or motor drivers, monolithic motor drivers. What this means, we will see in a separate chapter later on, where we will see all the differences. With these power stages, we are able to drive these different kind of motor applications, which can be found inside a heat pump application. Those motors can be driven by motor applications can be driven by either by BLDC motors or steppers or solenoids or whatever, depending on their exact needs. We will focus in this application reference design mainly on 3-phase BLDC motors. And on the AC front end side, as we said in the beginning, we have an active PFC solution. Normally, in order to fulfill the legislations for the grid connections. All of this power will not work without any brain. So the STM32 as a microcontroller is here the brain of the entire system. As this is a very sensitive part with very low voltage and very low power, we need also a signal conditioning to arrive from the high voltage levels here and high current levels to the very small signals computable by the microcontroller. Also, in order to understand how the condition of the application or the environment or the process is, we need to sense different kind of signals, which can be used for the regulation of the system. The system itself has to communicate either wireless or wired with other communication partners, and here we are offering also a wide variety of different products. Every application has normally a user interface, and also here are products from STMicroelectronics to serve these application needs. And for the application to communicate in hardwired with traditional digital IOs, we have also I/O signals or I/O transmitters, either inputs or outputs for the communication with other devices. And of course, low voltage will not work without any auxiliary power supply, which comes from the main grid to the low voltage or extra low voltage. As you can see, the screen is completely full with dark blue blocks, and that means that are all product blocks which can be supplied by STMicroelectronics. So STMicroelectronics can help you to address your entire heat pump application.
I guess that's over to me now, Andreas. So from a Würth point of view, I guess on that same reference design or application, we have got a wide range of products also that can be supporting the various functionality that Andreas has kindly explained for this reference design. So starting from the front end side of things on the AC main single or three-phase, of course, a wide range of EMC solutions in the form of common mode chokes, in addition to things like disc varistors, single or three-phase common mode chokes, I should add, as well as film capacitors. And as you go in, of course, on the AC/DC front end, which is this interleaved boost topology, we have got the FPFC choke, as well as the DC link capacitors. From an auxiliary supply side of things, which we'll also be talking about later on today, we've got a wide range of transformers as well, flybacks, forwards, push-pulls. So we'll talk about the importance of those as part of this design from an EMI point of view, as well as, of course, the standard functionality. And looking at the output end of things from a motor application side of things, again, DC film capacitors and rod chokes as well, for filtering side of things on that side. With the comms, as Andreas mentioned, the brain of the operations, be it the MCU side of things or the whatever communication protocols are used, there are a wide range of different filtering solutions in the form of low voltage common mode chokes, chip bead ferrites, as well as a wide range of transient voltage suppressors as well. These are geared for the various different comms interfaces, be it USB, LVDS, RS-232, 485, etc., that you might be using for this type of application. So there's an adapted type of filter topology. And that sort of covers the generals from a passives point of view from the Würth side of things.
Thank you very much, Mohammed. So if we now take a look on the general motivation, we saw in the past years that there were many moves done by the legislations in order to prepare the world, or in specific now here Europe, for the transition to abandon the fossil fuels for the heatings in the residential homes in order to become CO2 neutral, or to reduce the greenhouse gas emissions, or in some other parts, some other aspect was also to become more independent from the gas supplies from some certain countries, and as gas and oil supplies. And therefore, the legislations put in some incentives and new requirements for new buildings, for instance, and let's say the heat pump application itself is one very good candidate which can support this transition into a let's say a greenhouse gas reduced emissions future for everybody of us. In the market, there is, let's say, a variety of suppliers, of course, available. And what we can see, the application itself has been split into a few common system topologies. In our reference design, which is the basis here for this technical evaluation of this seminar, we are considering an air-to-air heat pump. Yeah, so that means the heat is extracted out of the environmental air, air-to-water heat pump, sorry. It's extracted from the outside environmental air and is converted into heat into the water part, into the liquid part inside the house. So air-to-water heat pump. Sorry for that misspelling. So, and normally these air-to-water heat pumps can be either in a split topology or monoblock topology build. So if it is a split topology, that means you have an indoor unit and you have an outdoor unit. The outdoor unit is outside in the garden and the indoor unit is somewhere in the building. Or if it's a monoblock, then everything is installed in one unit that is mainly installed then only indoors. That's the main split for heat pump systems, which we could observe on the market. For the indoor unit, as it has some control and motor drivers also, it has mainly an inverter application, which is the circulation pump. One or several circulation pumps are driving the internal water circuitry to circulate the hot water inside the building. For this kind of application of circulation pumps, STMicroelectronics has products like intelligent power modules out of the Slim Nano family or the PWD family. If we come to the higher power supplies, higher power requirements, which is normally in the outdoor unit, we can see a differentiation between a single home, so single residential, or large residential, or in terms of apartment blocks or even commercial buildings. Commercial buildings and apartment blocks, of course, have, due to their larger sizes, a larger heat demand. So that also calls for different kind of starting methods of the high power motors, especially if you have really large applications. Then today is very present still a traditional direct online, let's say on-off function of the outdoor units of the compressors or fans, or soft start is also coming. But what we see also as the next move, as the next iteration, that there is more inverterization to observe. Yeah. So more and more inverters are used to drive all of these fans for the outdoor unit, as you can see in the background picture. For the fans, STMicroelectronics offers intelligent power modules of the Slim Nano family. And for the main power device or power application inside a heat pump, the compressor, STMicroelectronics offers different products, either intelligent power modules, Slim family, or power modules, DMT32 for instance, or discretes. So here's example for HU3 Park or ACEPAC Smith. Beside that, we have also traditional packages like D-Square Pack or H2 Pack or TO247. So ST has a wide variety of power components. And all of those solenoid drivers, which we saw here in several places, those are typically low voltage applications, so they can be valves, either BLDC motors or steppers. That's very common. And here we have monolithic motor drivers of the ST Spin family. This goes now over to my colleague. Thank you.
So, as soon as we in the application lab have recognized this opportunity to help the manufacturers design in easier the power components, we set out to design a reference design to help in this way. First, we decided to base this design around a single home, like you can see on the picture here. It's an example of a modern building with standard isolation, which would typically require a thermal power in the range of around 7 kilowatts thermal power for an air-to-water heat pump. And with the current state-of-the-art of the heat pumps and their COP, the coefficient of performance of around 2 to 4 in these calculations, we can say that this would require around 2 to 4 kilowatts of electrical power to provide this amount of heating. So we set out to supply this design with just a single phase input of 230 volt AC to make it easier. And this would be possible to supply with a 16 amp circuit in a residential home. And we also set some targets for this reference design to make this design more usable for the manufacturers and more relevant. And this is to pass the European EMI regulations with this reference design and the current harmonic standards. And also to achieve a relatively high efficiency, which I think would be expected from a modern heat pump from a European manufacturer. So this then in turn gives us some requirements on the hardware and software of this design. So we need to drive two motors, one compressor motor, relatively high power, in this case 3.5 kilowatts, and one auxiliary motor for the fan, which would blow air through the heat exchanger of the heat pump, in this case 100 watts. On the input side of this design, we are mandated to have a power factor correction circuit, in this case an interleaved dual boost topology. Then to pass the EMI regulations and to make sure that we can pass them, we designed in a widely customizable EMI filter with cooperation with Würth Elektronik. And we've also got some need for some interfaces for the communication, for the sensors, and some auxiliary drive circuitry, and also an auxiliary power supply. And we also decided to show that we can control all of these features with a single MCU, and that means driving both the PFC and the dual field-oriented control of the motors with one MCU of the STM32 family. So the result of this work is reference design like you can see here. It is already available to selected customers and has already been shown in a few trade shows. And let's now look at the power design of this board, which is what concerns us the most. And this is a simplified block diagram, starting on the left with a single phase input, as mentioned, rectified by, in this case, a standard silicon bridge rectifier, followed by the PFC stage, the dual boost, with silicon superjunction MOSFETs and dual silicon carbide diode in one package. This provides the DC bus voltage that is then used by the inverter stages, and these are of the IPM type, the integrated power module, with IGBT switches. One is a 30 amp variant for the compressor, and the other one is a 3 amp smaller package for the fan drive. This is augmented by some other circuitry like the AC/DC auxiliary supply, the gate drivers, and some signal conditioning as well. It is absolutely mandatory, and it's all available from the ST portfolio. And to show that we didn't just leave this design on the paper, we can show that we took this design to the EMC chamber, and we managed to make it pass the regulations for the household appliance as specified by the CISPR 14 standard. We also evaluated the efficiency, as said in the targets, and evaluated fully up to 3.5 kilowatts, and the peak efficiency we recorded was 96.8% from the input to output. That means losses in the EMI filter, the PFC stage, and the inverter stage. The peak efficiency with this design was 96.8%, which is 1 percentage point increase over the same topology, only using IGBTs and ultra-fast diodes in the PFC stage. So with just two changes in the PFC stage, and only one of them being a silicon carbide device, we can achieve 1 percentage point increase in the efficiency, which is nothing to deny if it's this simple, in the high 90s percentage of the efficiency. So I will give the control back to Andreas for the next part.
Yes. Tak. Thank you very much. So let's take a look into the integration approaches. I mentioned in the block diagram at the beginning that STMicroelectronics offers different ways how to realize the motor inverter. So So let's start by make a split of these of the main blocks where we can apply this kind of integration. That's the control unit, so meaning the microcontroller, the analog part with the gate driver, and the power stage with the power switch. So in an all discrete version, we can split between a high voltage solution and a low voltage solution. So because we have different product families for these two different voltage rails. Low voltage, for instance, means voltages up to 100 volt DC. High voltage is up to 1200 volt DC breakdown voltage. Okay, so we have in the all discrete version, we have one package for the microcontroller, another package or packages for the gate drivers, and more packages for the power stage, which can be either IGBT, MOSFET, silicon carbide or silicon MOSFET, gallium nitride HEMTs, or a power module, which has only the switches, but not the driver, right? So that's why I consider that here as part of the all discrete. If we make integrated control, so we integrate the microcontroller and the gate driver into one package, then we call that an ST-SPIN32 approach. And here we have products for high voltage application and low voltage application available. Then you have all of these gate drivers, for instance. If you think about this kind of gate driver, this is just a half bridge, or this is a single gate driver on the picture here. So you would have 6 packages plus the microcontroller package merged into one package. And then you attach your power switches to that, whatever you need, with all the flexibility. Same applies for the low voltage. And the other integration approach would be intelligent power module or monolithic motor drivers. Here's also a small but very important difference and we see that in the voltage rails. So intelligent power modules need again the traditional standalone discrete microcontroller, but they converge the gate drivers with the power switches. And here the families are called SLIM or PWD. The motor drivers, we call them monolithic motor drivers because they are on a single chip. So it's a single chip, while these packages contain several dies, several chips inside. So you have your 6 switches plus the gate drivers and so on into the package. And here is one single silicon chip integrated into one package. And that's also one of the reasons why we offer these products of the ST-SPIN family only in low voltage applications. So what is now the good or the bad between these different approaches? Okay, let's take a look here. So in the all discrete version, as said, you have microcontroller, gate driver, and the power switch as independent devices. And here are just some examples of some packages. They are not fully exhaustive. It's just for visualization. So what is good? You have full flexibility to customize your application. You can optimize it to the best switching performance or energy efficiency performance. It is scalable because you can scale across the same package with smaller and higher currents, and you can choose even between different technologies. For instance, you can choose IGBT or silicon MOSFET, or even you can go to silicon carbide MOSFET, right? So depending on your exact need, so you can very precisely go to optimize the specific point of your application needs. And you have the wide choice between the different packages. So you can choose between through-hole packages or surface mount devices. And you can choose the cooling approach. If you want to cool through the PCB, bottom side cooling, or if you want to cool through the top, so top side cooling. Here, for instance, for the top side cooling, we offer packages like the AQ3 pack. But there's always a but. But it needs space. It needs more space because you have the space around the device, the circuitry around, the gate driver around. So you have many components to place. And the way how the heatsink has to be attached, either if it is just the PCB, which is acting as the heatsink, maybe you want to attach also a heatsink to that. In some applications, this is also needed, or you have the heatsink on the top. But the main con here is the electrical insulation, because most of these packages have no electrical insulation. So you need to provide electrical insulation maybe either through a specific package with embedded electrical insulation. For instance, here we offer full pack packages here in the TO220, these are TO247. Or we have AcePack Smith, which is a topside cooled surface mount device, topside cooled, I said, and electrical insulated. So that is also a possibility, right? So one alternative could be the integration of the microcontroller with the gate driver. So here you have already reduced all the gate drivers and the interfacing to the gate drivers. So the wiring, everything is already set. The microcontroller is already pre-wired internally inside the package with your gate drivers. So that's significantly less components on your PCB. You see here, this is the gate driver on that board. And this is the ST-SPIN32, sorry. On the board, there's no gate drivers because there are the D-pack packages here. Okay, and then you have the 6 packages. You keep your flexible switch selection so that you can choose whatever kind of switch you want to use. If it's a MOSFET or an IGBT, this is very convenient. And you can still participate from a relatively low BOM count. So few components only to adjust. And you keep your adjustable gate driving. So you can adjust the switching profile as you need for the application. So this is an integration which is very, very compact, and it's very good if you want to integrate your inverter PCB into the motor body. So in motor integrations. But the microcontroller is limited by the pin count on the package. So we have a very limited amount of GPIOs available because of the prefixed package, and due to the discrete packages, you do not have any inside temperature detection, right? So you have an external temperature detection need on the heatsink or near the PCB, near the device, in order to see where how the temperature is in your power switches. And you have not the same amount of microcontroller variants available as STMicroelectronics offers in the standalone microcontrollers. At the end, we can say that this kind of integration with the discrete switches is more related to low power applications, for in motor low power applications. Last but not least, the intelligent power module or monolithic motor drivers integration approach. We combine them here because the idea here is the same for monolithic motor drivers and for the intelligent power modules. It's the same idea. You integrate kind of the driver, if it's a logic for the integrated motor, for the monolithic motor drivers, it's a logic, driving logic embedded, and also the power switches. Yeah. So this gives you the integration of the entire power stage in terms of driving and switching. And you have still the discrete microcontroller. What is here the pro? Space. Because here you save the most space, because what needs the space is the separate component placement and the gate driving. So that is here solved in a very compact package. That means at the end, the total cost of ownership can be least, because you have to attach only one heatsink with two screws, right? Or with the monolithic motor drivers, you cool through the PCB. The thermal management is easier because you have already electrical insulation through the package. And you have an accurate temperature detection, for instance, by an NTC, if we think about the intelligent power module. The monolithic motor drivers, they have an over temperature protection embedded by default, so they will also disable if they become too hot. But there's always a but. But due to the nature that these are completely encapsulated and integrated devices, the gate driving is fixed. One thing is for sure, we as STMicroelectronics, we always design our products for the application. So we also consider in this application requirements the gate driving needs, so that we do not switch too fast or too sharp, we could say also. So there's an adjustment done on the gate driving profile. So there is always optimized, our modules are always optimized for low emissions, high efficiency, and so that you can be sure that we make the best compromise between the switching and the performance. But those are also mainly for low to medium power only, especially when you think about monolithic motor drivers, they are also only for low voltage applications. All in all, as a conclusion, the intelligent power module is good for high power density, and because of the integration, it is good for a fast design to market. While the ST-SPIN32 approach is good for space-constrained applications if your PCB location will be inside the motor or very near the motor, where you only need to care about the signals which are relevant for the motor itself. If it is a position feedback or a temperature sensor, so just a few signals to collect. That is very good with the ST-SPIN32 approach. The motor driver is best for the maximum miniaturization of, for instance, of valve applications, because they are low voltage and low power. The discrete is good for all approaches where you want to approach multi-sourcing and let's say to be very flexible, and you want to reduce the BOM cost at all. So that's one reason why discrete is still very popular, and it's for medium to medium power, and if you have only no space constraint. So that's the point.
Okay, since we are this time focusing on the heat pump reference design, the following chapter will focus on the IPM approach, as described by Andreas. And as an application engineer, most of my work revolves, pun intended, around signal integrity and EMC. This I see as one of the most challenging parts of inverter design. And since we have an expert from Würth Elektronik today with us, this is what we will focus on in the following chapter. One of the biggest tools I see as an application engineer or as the designer of the inverter, one of the biggest tools we have to combat the signal integrity problems and EMC is the layout. So let's see what we can do in the layout. Let's see what we can do from the beginning of designing the inverter. Let's give you some steps you can follow to make sure that you don't run into some problems later. And the first one, at the absolute beginning of the layout stage, it's a good idea to lay out the blocks of circuits and separate them by their function. That is just common sense. And then it's also important to think of the blocks of circuits as either victims or aggressors of the interference that is inevitable in an inverter. In an inverter, it can be pretty much simplified, because you can say that most of the high voltage circuitry is likely to be the aggressors with the fast switching that has to happen there. And most of the low voltage circuits are going to be rather the victims of this noise. So it's a good idea to separate them into two different stages, two different regions on the PCB. But even so, there are always going to be some meeting points of these two regions, because, for example, you need to control the high power stuff with the control signals from the low voltage section. Next step is, in my opinion, one of the very important ones, and that is to ensure ground reference uniformity. This means that if you design your board to have multiple ground regions, for example, if you prefer to have separate grounds for the digital and analog circuitry, then it's important that these two regions, although they are a little bit separated, that they all have the same potential, or as close as possible to this situation. And in my opinion, this is achieved well with a star grounding approach, which means that all these separate ground regions all reference to a single point on the PCB. And this way you avoid having some ground loops. This is always a bad idea, and it's good to reference this point to a stable point on the PCB. It is not always possible to achieve this completely, and if you're facing some difficulties with this grounding layout, it's a good idea to consider using signal isolators between the different ground domains, or differential signals, because differential signals don't care about the common mode noise that would appear on the different grounds. And if the noise isn't severe, then maybe just some filtering on the signals between different ground regions may be enough. Next, since we still have all the maneuvering room on the PCB, we can focus on the power traces, because these are likely to be the most aggressive noise sources. So let's optimize them first while we still have the maneuvering space. And do this, we can route the traces as close as possible to each other, to the positive and the negative tracks as close as possible, to minimize the loop inductances. This is important to reduce the noise radiation from these traces, because the smaller the loop area, the smaller the inductance of this loop, and the smaller the magnetic coupling to the neighboring circuits. It is best to route these traces on top of each other, if possible. If not, then the closest that your clearance and creepage standards allow you. Once we have the noise sources, most of them placed on the PCB, and optimized to radiate as little noise as possible, we can focus on the victims of the noise. And these are the low voltage signal traces. It's always a good idea to keep away from the noise sources. Well, this is just common sense. But in a more concrete example, this means keeping away from the high DV/DT nodes. That means the high switching, the fast switching nodes of, for example, the PFC and the inverter, and the high DI/DT loops. That means the loops where the current changes rapidly. And also, a thing to keep in mind is the return path of the signal, because the signal never flows just between the output pin on the MCU and the input pin of the IPM, for example, but the signal always has to close the loop. This is usually in a single-ended signal through the ground. And this is where the ground uniformity comes into play. And then you build your first prototypes, and even if you tried your best during the layout stage, just be prepared to repeat the steps 1 through 4 and improve on the existing design, because rarely this works on the first time. Now let's look at some concrete examples of these advices. You can see here an example of the schematic around the integrated power module, mostly taken from the datasheet and the application note. And on the right, you can see this exact schematic laid out on a PCB following the guidelines. You can see in the middle the IPM, to its left the filtering of the signal inputs and the decoupling of the gate driving voltage. On the right, you can see the DC bus ground capacitor placed as close as possible to the IPM to minimize the inductances between the capacitor and the input pins of the IPM. And the overcurrent comparator and the DC bus capacitor on the bottom. On the bottom right of the screen, you can see where the start point of the grounding would be if the MCU ground and the IPM ground have to be separated. It's best if they are connected together, if they are the same ground. But for example, in the case of the heat pump reference design, there are 2 IPMs and the PFC stage, which ideally would all be on the same ground, but this is not possible. So there has to be some start point, and this is where it would be. The IPM, the integrated power module, solves a lot of the complexity of the layout of the power stage because it integrates the gate drivers with the power switches in one package. Also, it sets the switching speeds, the gate driving, which is admittedly a double-edged sword, but this is what it is, and it most of the time it works in your favor. But still, there are some things to keep in mind. Otherwise, the integration and the low inductances inside the package may come in vain if you don't pay attention. And this is mainly in the gate driving, loops, and the loops that the current from the gate and to the gate has to take during the turn on and turn off of the power switches. On the high side switch, you can see on the left that this is pretty simple. The turn on current closes through the bootstrap capacitor, and the turn off is absolutely internal to the device, which translates on the layout to very small circuit loops, which means low inductances, low noise radiation, and low noise susceptibility. On the low side, on the other hand, the situation is a bit more complicated because the driving current always has to pass through the shunt resistor and through the main ground. And this is why it is really important to reference the ground of the IPM gate drivers to the same ground as the shunt. This creates the smallest signal loop that you can achieve, and this avoids having problems with the switching and noise coupling to the whole rest of the board. There are also other signals to care about in the IPM design, and these are, for example, the PWM signals. These are digital, and these are the most robust signals on the low voltage side. So these don't usually require that much care. But still, if the IPM doesn't have protection against the shoot-through, it still might be beneficial to include some filtering and care about the design. There are also the current sensing signals, because in every motor control application, you need to sense the currents through the phases of the motor. These signals are usually quite low voltage, low magnitudes, but also they are low impedance. That means that the noise couples to them a little bit less than to that signal that would be high impedance. An example of a high impedance signal would be, for example, the temperature signal from the IPM. This is usually obtained from an NTC, which is itself a high impedance. But in this case, the time scale of this signal is really long, so it's easy to filter this signal afterwards. Okay, so what is the noise actually coming from that you can measure on the signals and that you have to tackle? It can be separated into three categories. The first is the inductive coupling coming from rapid changing current in the nearby current loops. Second one is capacitive coupling, coming from high rate of change of voltage in the neighboring voltage nodes, coupling through parasitic capacity to the signal. And the last one is the galvanic coupling, which comes from sharing the signal with other signals and depends on the resistance of the shared path and the inductance and the rate of change of the current in that part. So what can we do against this? Well, in the most simple case, it will be just adding a filter that shunts away most of the high frequency noise. That is usually higher frequency than the control signal you're trying to pass to the IPN, which can still pass through the filter, mostly unattenuated. This is mainly a fix for a problem that shouldn't be there in the first place. And this can be done by minimizing the loop area to minimize the inductive coupling, keeping away from the high DU/DT nodes to minimize the capacitive coupling, and reducing the area of the traces between each other to minimize the capacitance, and avoiding shared ground paths because this creates the galvanic coupling. This is an example of the mentioned problems on an actual PCB, and the same example as before. You can see the path that the signal has to take from the MCU to the IPM through the star point of the grounding and back to the MCU. This is the less ideal case when the star point has to be there and the signal has to close through a relatively large loop. But since these are, in this example, digital signals, they are relatively robust and can take this amount of galvanic coupling. The rest of the noise that is coupled onto this trace, the capacitive and inductive, is partly filtered by the added RC filter, and this should be placed as close to the relevant input pins as possible and grounded to the same ground that the receiver is grounded to, in this case, the IPM ground. This way you can shunt away all the noise that is coupled in this whole loop. When it comes to the current sensing, there are also a few things to keep in mind. It is good to prefer differential sensing because in cooperation with the op-amp, in a differential amplifier configuration, this attenuates the common mode noise that is coupled onto the two signals. So these two don't get passed to the MCU. It is good to use Kelvin connection to remove the effect of the added resistance and inductance of the traces outside the shunt resistor. And it's good to route the differential signal as close to the MCU as possible, because this way you avoid as much of the common mode coupling as possible. And a side note, it is important not to overfilter when trying to filter the current signals, because this would in turn degrade the performance of the FOC algorithm that needs to have an exact measurement of the current at the exact times. And one final piece of advice: when tackling EMC issues, it is a good idea to model, or at least in a simplified schematic like this, the whole setup that measures the EMI and the coupling of the noises in such a setup. So this is the setup you would have in the conducted emissions measurements, with line impedance stabilization network on the left, the device under test, this inverter in the middle, and the connected motor on the right. And you can see highlighted some of the parasitic capacitances, for example, that would contribute to some of the common mode noise that is measured on the listen. And in this way, you can get a small glimpse into why the results of the EMC look what they look like. And for example, in this case, we managed to explain this peak in the EMI spectrum and correlate it to the series LC resonance between the inductance of the wires to the motor, the capacitance of the motor windings to the chassis of the motor, and the inductance of the protective wire of the motor back to the PCB, and then closing back to the output phase where there is a high rate of change of the voltage, which causes a ringing in this LC resonance circuit. But this is more of the expertise of our colleague here from Würth Elektronik, Mohammed. So
when we started talking about the system that we have got at hand now with this reference design, we were looking at the relevant standard to follow from a compliance point of view. And that was identified earlier by Andreas as the CISPA 14, basically, N55014, parts 1 for emissions and part 2 for immunity. Of course, global other standards will also apply in terms of FCC in the US or the CTIC mark, sorry, I beg your pardon, Australia, New Zealand. But in general, from a emissions point of view, which is the work that we have done on this board, we have followed the CISPA 14 part 1 as our guide for measuring conducted emissions from this board. There were other tests as well that were performed, I believe, on this board, which are associated with harmonic content, basically, which is the EN61000-3-2. Now would be the applicable one because it's less than 16 amps. Now, if you've got something that is higher than 16 amps, it would be -3-12. And for voltage dips and interrupts, again, it's the same -3-3 or -3-12, depending on your voltage rating or current rating, beg your pardon. So this is the general overview from a class point of view, again, depending on where the application is installed. So if this is a residential home, like the picture we were shown earlier on, with something that applies on an internal circuit breaker in your household. So class B would be the limits, which tend to be more stringent than class A, which is more used for commercial, industrial type applications. So these were the set limits that you also saw in some of the EMC test results that Hendrik has shown, as well as Andreas. Okay, so absolutely correct. Without layout and tracking, without good layout and tracking, you can't achieve EMC compliance. This is an absolute must. And I will be referring back to layout and tracking as well. But in addition to that, naturally, with this design as well, we had to include some kind of filtering as well. So what we will be talking about in this next few slides is just a few of the filters that we have implemented for this design. So from a single phase AC mains, you can have a single stage filter with a common mode choke, as well as 2 Y caps, as you can see here, from the live neutral down to earth, as well as a single X capacitor across the mains. The single phase side of things is really applicable for what we are looking at now at around 7.4 kilowatts maximum throughput power onto your load. You can also use a 2-stage filter where we duplicate basically the filtering across again. So that gives you a much higher insertion loss naturally, and provides you with the level of attenuation required. This is very much reliant on the type of topology that you're switching and how clean your supply coming back is. One thing that is beautiful about this type of architecture, single or double stage, is, and maybe something that's missing as well, is where's the differential? I've talked about common mode stage here. I've talked about a capacitor as a single 20 dBs per decade filter. Is that going to be sufficient? The nice thing and the beautiful thing about this is these common mode chokes also provide you with leakage inductance. So that also acts as a series L, if you want to call it that. Let me just use the laser pointer. So it acts as a series L here with this T that gives you a 40 dBs per decade. So it's a freebie, which we don't usually get in electronics, but that's a really nice thing to have. So that's a single phase. If your power levels exceed 7.4 kilowatts, if you're more in an industrial type environments, 22 kilowatts and above, charging, for example, then you may need a 3-phase type filter with a 3-phase common mode chokes, again, showing the Y capacitors here connected down to your ground, reference ground. This is the common mode, single double stage filters, and the same would apply for the differential side of things. The difference here is, of course, you've got X capacitors, be it line to line or line to neutral, depending on the connectivity of your mains 3-phase input coming through. The Y capacitor, as well as the common mode chokes, will act as your common mode insertion loss filter side of things. Again, the leakage in this setup will also provide you with at least a 40 dBs per decade insertion loss. That's what we will see on the next slide here with the leakage inductance and the X capacitors working together to give us at least a 60 dBs with a SPI filter that we have got set up here. And this is in green, the common mode filtering that we can also achieve with these Y capacitors and the common mode choke, the 3-phase common mode choke as well. You can offset the values of these caps here to cover a wider or a more broadband range of frequencies. That's what we mean by big and small here. So we mentioned on the slides, the small capacitors are something of the order of 1 to 10 nanofarads. This is more in the region of 100 nanofarads or so. And that gives you a sort of a wider bandwidth of an insertion loss for that filter to cover a wider range of frequencies. Oops. So considering a little bit more the type of common mode choke, be it for single phase or for 3-phase for that matter, the type of material makes a big difference as to that bandwidth of insertion that you get, because yes, we are concentrating very much on conducted emissions here, 150 kilohertz to 30 megahertz, but the material does make a big difference as to how it performs. So if you look at the CMB range, for example, which is this red line here, that's a manganese zinc based material, which is more optimized for the conducted emissions range. So up to 10, 20 megahertz or so, and then it tails off as you approach the 30. If you're looking more for the radiated end of things, then it would be more the nickel zinc type material, which is optimized 30 megahertz upwards of. And there's also this nanocrystalline type material, which is a much wider broadband type material, covers both conducted and interradiated up to 100 megahertz. So this is the optimization of the selection of the type of common mode choke that would be utilized for this type of application. Okay, Jacob has mentioned, about the boost converter, the interleaved boost that is used for this heat pump design, inverter design, as a supply coming in off the mains. I just wanted to identify again some of the key points on this design, on this boost design, that we need to take care of when it comes to layout and tracking, when it comes to filtering. So the hot node is the switching node naturally across the main FET and a boost topology. And the hot loop is the output loop here, which carries the very high DI by DT type signal. Now, regardless of you're using transition mode or continuous conduction mode, you're still going to have a very sharp rate of change of current differentially, and a high dV by dt naturally across that device as you switch it on and off, depending, of course, on the switching frequency as well. So the harmonic content of this signal here is fairly high. And with these harmonic contents, that's what can result in both different types of noise, differential and common mode. Differential tends to be related more to your current loops, and common mode is what is either radiated of your tracks, of your heat sinks, etc., or cables or harnesses within your system, or actually just coupled capacitively across onto heat sinks and other tracks and signals within your board. And that's what we're trying to show in terms of what creates common and differential mode. I will come back to these types of noise currents when we come to talk about the flyback topology, which is also something that is used on this reference design in a little bit. So with this boost converter, just to also maybe reiterate some of the points that Jakub has mentioned, if you do not include the right type of components, filter components in the topology, and I'm not talking here extra filtering, I'm talking about the standard output capacitor in this boost. This is just a simple boost converter that we have designed. It has nothing to do with this heat pump design side of things, but it's just trying to show the impact that this is have with the high dV by dt and di by dt nodes and loops on the actual performance of the board. We've built this board, and excuse my language, but we've done a really bad job, dog's dinner, of laying out and tracking it with the purpose of trying to show how bad this can be. And we ended up looking at the output voltage on this board here with 12 volts peak to peak noise ripple on the output. So this can become a massive issue from a layout and tracking point of view. I guess the point has already been made earlier by Jakub, but also from a very important point of view here is the selection of the right type of component is what I'm trying to also get to. The right type of capacitors, the right type of inductors. Don't want to jump the gun just yet because I will be talking about those in the second presentation that I will be doing. So that's the boost side of things, the flyback. And why do we talk about the flyback in particular? Because the auxiliary supply that is used in this reference design has got a flyback converter. It's the flyback topology that is used, and it is based on the Viper 26 LD, if my memory serves me right, which switches at 60 kilohertz. Again, if my memory serves me right. So just to give you a brief background on the flybacks, because the flybacks, simple topology, very nice power topology, especially for low power levels, which is what we're looking for here. But it can contain or can produce a lot of EMI noise. So just trying to identify some of the noise sources and where it can come from, so we can link that when we come to do the testing and optimization of this board in order to achieve compliance, to achieve a pass from a conducted emissions point of view. You'll be able to link some of what we talk about now in terms of noise sources and what we will see later on as we do we perform the iterative testing on this reference design. So a flyback converter, for those of you who haven't heard of, it's a buck boost isolated topology. So 3 modes of operation. So you can either operate in continuous conduction mode, in which case the device switches on, you store energy in the primary, and then the capacitor delivers energy to the load. You turn the switch off and energy is delivered from the secondary side, charging up the capacitor and powering up the load. If this current is continuous, so it does not drop down to zero, basically, so that's continuous conduction mode. But if the energy in the transformer or coupled inductor, as it's supposed to be called, formally drops down to zero, so there is no more energy, the capacitor then delivers that power to the load, and you are in this continuous conduction mode as shown here. So in the Viper 26 chip, we primarily operate in this continuous conduction mode. So looking at the actual model for this flyback converter and identifying all of the parasitics around it is very key. So this is always a good starting point, even before you've managed to lay out and track, is to draw a diagram like this, where you are able to identify based on that function, whatever that function is. It's a microprocessor, it's an IPM, it's a flyback, it's a boost. You identify some of these sources, these parasitic components, in this case, interwinding capacitance, the output capacitance of a MOSFET, the junction capacitance of the diode, the ESL, ESR of the cap, etc. So with these as well, these would be the ones that would be causing your resonances, your frequencies that are outside the main switching frequency of your switching element or device, in this case, your FET. And accordingly, then you can look at how do we optimize our performance from an EMI point of view? How do we change the signature from a noise point of view? What are the practices for this type of application? I think some of these best practices were also mentioned by both Hendrik and Jakob when they talked about both the IPM side of things and the PFC and the PFC side of things. With the flyback, just as a very simple, something that you see in a lot of reference design is the inclusion of this Y capacitor across the windings. And basically that shorts out the interwinding capacitance of your transformer. So I will show you again some of these more elaborate parasitics on the next few slides. But this is a good starting point always. So identifying the hot loops and the hot nodes like we have done with the boost converter is something that is very critical, especially from a layout and tracking point of view, trying to minimize those. Identify where those currents would be flowing that can create radiated loop antennas coupling onto other tracks or loops capacitively through the high dV by dt or inductively through this loop through the high di by dt. So just showing you that setup for that particular type of converter, the flyback converter, and the pathway for common mode noise as a result of the switching of this node here. This is the high dV by dt node. So there is capacitive coupling. And by the way, all of these components that you see here are parasitic components. They're not physical components. So this is the interwinding capacitance of the transformer, a nice pathway for common mode noise to flow through the parasitic capacitance from the return into the reference ground of your enclosure and back through your 250 ohm resistors in your listen, being picked up by one of the two RF outputs coming out and being measured by your test receiver. And another pathway again through the parasitic capacitance between the FET, the drain junction of the FET, which is sitting on top of a heatsink with a thermal pad on top, creating a lovely capacitor. And again, that is providing that pathway back for common mode noise back to your listen, being picked up in conducted emissions, but this could also be radiated as well in higher frequencies. And the same concept again from a differential point of view. We have got the looping currents, and you can see also from a listen point of view where that differential current can be picked up from. So, okay, all of these are various different sources for noise. It is very important when it comes to the design of a flyback converter to consider filtering for some of these, using snubber circuits for some of these. We will allude to that later on in this session, just to identify for you where you can include some of these solutions. So just to show you a bit of the system that we have measured for the heat pump reference design in this test setup, which I believe is on the ST side. This is the EMC test chamber, so conducted emissions. This is the actual board itself. And that's the listen, the EMV216 listen, CISPA16. This is the SRP receiver, test receiver. And on here is we've got the motor and the brake acting as the load on the motor. And you can see the connection to the motor, the 3 phases. And this is the mains cable connecting out from the listen. Next, naturally, as we have mentioned earlier, we have tested this based on the CISPA 14 standard from an emissions point of view. And starting off with, so just going through, and I'm not repeating every test that has been done on this, but I'm just giving you snapshots of some of the improvements that we have done and some of the steps that we have taken as we were performing this testing. So the initial test was with the board powered on. The Viper auxiliary supply had this transformer. We call it an old transformer because that had to be changed because that was a source of some of the noise that you see here. The MCU was running, but neither the PFC or the IPMs were running. So they were off. And that setup here was with the heatsink ungrounded. Which heatsink is that? That's the heatsink that we have under this board here. You might not be able to see it very well, so I do apologize. So there is a heatsink here that the actual board is mounted on top of. And again, we had a long unshielded motor cable. You saw that cable that we had connecting the actual reference board to the motor, and no ferrite clamps. And the first peak that we saw under this was this 800 kilohertz, which gave us a bit of a failure above at the peak, quasi-peak limit. And that was associated with the flyback oscillation. So that's where this transformer was creating some noise, or the old transformer was responsible for some of this 800 kilohertz noise that we were seeing. The next step was to start running the IPM. Sorry, the PFC was still not running. Everything was still the same. And now we can identify a 2 megahertz as a result of the IPM side of things and the motor cable, because that's what's connecting the intelligent power module, to the motor. So that's the next peak that we saw as a result of, and that was at 2 megahertz. And the final step that we have done is with everything running. So that's still with the old transformer. And now we also have observed a 12 megahertz, and that was attributed to the PFC side of things. So with these sort of three separate starting different parts of the system, you can identify or help yourself identify some of where the noise is coming from. Next were a whole series of different improvements that were done to the design in order to try to reduce some of the noise that we were seeing. One of them is changing the transformer, and I'll explain why we were changing that flyback transformer. Grounding, for example, the heatsink to the Y-cap center point. The motor was grounded to the Y-cap center point. We used a shielded cable, which is a much shorter cable as well, between the motor and the board. We used also ferrite clamps on the input supply AC mains and the output to the motor. And we also optimized the input filter as well. So that has resulted in these improvements that we see here across the whole frequency range. So if you see, where is it? Let's go here. So this is where we started after having done a lot of the changes on the board itself and with the shield, with the cabling as well. And this is where we've ended with all of the various different improvements also being implemented below the line. So it was a good pass. And that is the filtering on the input side that I mentioned that we had also optimized as well with the manipulation of some of these values of filter capacitors. Going back to the transformer or the flyback transformer side of things, the change was from this to this type of transformer, and the main impact was that interwinding capacitors. If you remember back to the parasitics structure that we shown earlier, that interwinding capacitance acts as a very nice pathway for common mode noise to flow through the transformer, find its way back out. So in order to optimize that and minimize that, we have introduced this a new transformer with a much lower interwinding capacitance. So from a filtering point of view, again, I've just shown you the filter stages. We used a 2-stage filter on the mains input. Different types of materials can be quite useful. If you can afford a 2-stage filter, this would be amazing because you can use the low frequency optimized type manganese zinc material and then the high frequency optimized nickel zinc material and cover a much wider insertion loss across the entire frequency range. If space is of the essence, if you can't afford that, nanocrystalline would be also a good type of material. That's quite a wide broadband material, and maybe you are able to do this in a single stage. But it very much depends on what your EMI signature looks like. Couple of maybe quick slides on this specifically with regards to layout and tracking. The EMI section side of things, a key recommendation for us is not to place any tracking under the filter components so that you do not get any coupling capacitively through those common mode chokes across. So you can see here there's daylight across the the common mode chokes so that there is an optimization of the impedance or common mode rejection across that common mode choke. Another aspect, I think Jakob has talked about this in detail. So it's minimizing the hot loops on the PFC stage, on the boost stage. But one thing that also can be optimized on the boost side of things is the inclusion of a common mode choke on the output here. Now, the common mode choke, as I've mentioned before, acts as a 2-in-1 for you because it gives you the common mode insertion loss, of course, but it also gives you that leakage, and that leakage inductance with these output caps as well that you have got here will provide you with another LC, another divide by 140 dBs and surge attenuation of your output ripple. So it'll improve things from an output point of view, an output ripple point of view. Also another thing as well, and Jakob also mentioned this, the reverse recovery of the diodes at the output. Sometimes we also put a provision for some snubber circuits across that as well. Going to the auxiliary stage, which is that flyback converter side of things. So that flyback is based on this, the Viper 26 chip. So we can see here we've got the snubber circuit across the primary of the transformer. So sorry, we don't show you the transformer here. But on the very input side, there's also a possibility of adding an LC filter here in order to try to clean up or further attenuate some of the noise that might be coming back from the actual flyback converter stage as well. So it's an extra LC filter that you can add in on the front end of that circuit. We have implemented on the output of the Viper chip a lot of filtering as well. So this is where the flyback ends here at the output caps, and we have got two 3.3 isolated voltage outputs as well as the 15. And with these we have included extra LC filters on the output here in order again to clean up some of that output voltage ripple. Flybacks do have higher than usual ripple naturally. So having an extra LC will do you a lot of good as well when it comes to that topology. Some of the various different layout and tracking considerations as well with that LC filter I've just mentioned earlier. That's the L. These are the two capacitors. So you directly track between the L and the two Cs before you go across into the next IC, which was that voltage regulator LDO. From a grounding point of view, we stitched down to the ground plane right underneath with a via to minimize any inductances associated with any track runs as well. So this optimizes the performance of your filter LC, Pi, T, whatever you're using. So as an overall sort of EMC improvements for that setup, what we have done is we have initially started off by using cable ferrite clamps on both the motor cable and the AC mains cable to try to identify what improvements need to be done and also what the noise sources are, whether it's these cables or something internal onto the board. The EMC solutions are, of course, in the form of designing in a two-stage input filter, which I showed you earlier, implementing the Y capacitors and their placement, with the shielding being terminated on the center point, on the reference ground or chassis ground for those Y capacitors, the cable shielding of the motor cable, making it shorter as well in length, grounding the heatsink to the Y caps, again to the same point as the Y caps center point, which is your protective earth, your ground or reference ground or EMC ground, and of course optimizing the flyback transformer. So with all of these implemented, this is the new setup, by the way. So this is with the shorter motor cable, which is shielded. Now this is with also the cable ferrites implemented on both sides, as well as all of the improvements regarding the grounding of the Y caps and the shielding of the motor cables. We have got, this is the final test results that we have achieved, which again is something that the guys have shown you earlier. And that's also, of course, with the new transformer being implemented for the Viper chip. side of things. Over the next few slides, on the next slide, we will be talking about a buck regulator just as an example. And by the way, the last section here, we're just trying to give everybody a feeling of the optimization of the selection of inductors and capacitors without particularly it being directly applicable to this reference design. But of course, with the selection of any component, you saw what we can offer on this design in terms of inductors, capacitors, PFC chokes, etc. This would be directly applicable for sure. So on the next slide, we will see just based on a simple buck converter, but this could also be a boost or a SEPIC or any inductor-based type storage topology. So the basics of a buck, as we will see on the next slide, is we have got a switching signal that's going through the power inductor that during the on time, the inductor is energizing, so current is increasing. During the off time, it's reducing. So this is what's called the ripple. And that's what you see up at the top with the the equation for that ripple percentage is the delta IL with respect as a ratio of the average current in the inductor. So this is important because we will refer to this ripple percentage later on as we go through and do some of these calculations. So if we go on to the next slide, we will see that that ripple percentage as it goes down. So as you go to 10% ripple, your inductance value becomes quite big. And that, so that's the one in red. That's the very small delta I basically. So that's great. You've got very low ripple, very good noise performance, very good EMI performance. But that means your inductance is big in inductance value and big in size as well. And vice versa. If you go in the other direction, if you make it too big. So on the next slide, we will see just an example based on the calculations that we've done for an inductance value with a 24 volt input, 5 volts output, 2 amps switching at 600 kilohertz, and a drop across the rectifying diode of 0.3 volts. This is the equation that we would be using to calculate the inductance value. This is fairly basic. Again, that includes that R value, that ripple factor, which is a percentage of I out, which is the average current through that inductor. So if we look further down, and we start the calculation for that inductance value based on the ripple factor. So we've got 3 different inductance values based on 20%, 40%, beg your pardon, first, at 8.6 micro, 20%. If we keep going, please, Andreas, yeah, that'll give you 17 micros, and finally 10%, and that gives you 35 micros. And if we look at the curve actually describing this, one last click, thank you very much. And that shows us that 1 over R, which is 1 over X type relationship. So actually, if you're going to really reduce your ripple percentage, you have to suffer a lot with a lot of inductance value in order to achieve that. So the moral behind this slide is the usual or default value that we usually go to is 20 to 40% as a ripple factor. So that's what we would take from this as a good halfway house between you having a decent value of inductance and decent size, of course, of inductance, and a small enough ripple across that inductance and a good enough EMI performance. So if you go on to the next slide, we can try to do the same with but from a capacitor point of view. Now that we have selected the inductance side of things, let's see if we can select the capacitor side of things. So with that, what we would be looking at with the capacitor is splitting the actual capacitance ripple into 2 components. One associated with the actual capacitance of the capacitor. The capacitor ideally is just a capacitor, but we know for a fact it's got an ESR as well, and it's got an ESL. But for today, I'm just going to model that capacitor as just a cap, an ideal cap, in series with an ESR. So we'll apportion that overall ripple to these 2 components, one associated with the delta VC, with the capacitor side of things, and one associated with the ESR. And that's what you see in the simulation results as delta V total. So in black, you will see the delta VC. In red, you will see the delta V ESR. And that's the overall contributions of the different portions. So on the next slide, if we go along, we'll just show a few equations. First of all, the overall calculation of delta V, the ripple across the capacitor. So the ripple across the capacitor is related to the capacitance value, the switching frequency, as well as that delta IL, because that ripple current that we have in our power inductor is going straight through into our capacitor. So that's that equation, delta V, and I'm not going to go into a lot of the calculations and the math side of things here. I'm just leaving this for your information to utilize maybe at a later stage if you wanted to. But the idea behind this is they're going to go step by step and eventually show you how you can optimize the selection of this capacitor. So over on the next slide, thank you for jumping across. All that we've done here is take the delta IL calculation that you see in the middle of the page and plugged it into that equation that we saw on the previous slide. Now we have got delta V as a function of the inductance, the capacitance, as well as the switching frequency. Everything else is a constant or is something associated with your circuit that doesn't change, V out, duty cycle, etc. So if we go on to the next slide, and now becomes another factor into the selection of the output capacitor, which is what's F0? That is the cutoff frequency of your output filter for an LC output of your buck regulator. This determines your plant transfer function cutoff frequency for your output filter. So this is the double zero, double pole at the cutoff, 1/2 pi root LC complex conjugate poles that you would get. So that's also part of the selection criteria for the L and the C, or from a C point of view, where if we've already decided on the L. So we need to take this into consideration, in other words. So what we have done now is taken that equation, F equals 1/2 pi root LC, very basic, and just plugged it into the previous equation. And now what we have is F0, which is the cutoff frequency of your output filter, as a function of your switching frequency, a constant, V out, D, pi, and delta V. And delta V is your input. What ripple would you like to see across the capacitor? That automatically would determine your cutoff frequency for your output filter. So now there's always a relationship between F0 and F switch. We usually say good to cut off a 1/10 below the switching frequency, a 1/5 or a 1/10 below the switching frequency is usual rule of thumb. So we will see how that works out on the next few slides. So let's move on to the next slide, please, Andrea. Thank you, sir. So on here, we start off with how we can now take this F0 and use it to calculate C out. Now that we have got C out is 1/2 pi F0 squared times L. This gives me my output capacitance value based on the ripple requirement that we have initially. So can you see now where we started and we finished? So all you need to have is your ripple requirement. And from that, you know your switching frequency. You can calculate your F0. From that, you can calculate your C out based on the L value that you've already selected. Let's move on to the next step. So as I said, we are going to apportion this into two different portions. The second portion is the delta V associated and attributed to the ESR of that capacitor. So that's very simply that resistance, ESR resistance, multiplied by the ripple current, the triangular waveform that you saw earlier in the inductor. And then again, we substitute for that delta IL. It gives us the equation circled in red down at the bottom. That gives you the delta V ESR divided by V out multiplied by L's F switch over 1 minus D. So again, with this, you enter your value of delta V as ESR that you want, and accordingly, you will know what ESR value you need to select a capacitor based on. So again, all will be clear on the next few slides. Moving on. That's two parameters now. The final parameter for selecting a capacitor. So we know the capacitance value, we know it's ESR that is needed. Now we need to know the RMS current that the capacitor or ripple current that the capacitor RMS ripple current is what I should say, in the capacitor that the capacitor can tolerate or can carry. And that's based on the equation that you see circled in red here. Now, just to point out, these equations are associated with the buck converter. It will not be the same for the boost or for a SEPIC. So you will need to recreate some of these equations for these other topologies as well in order to calculate the relevant values as I've mentioned them. So moving on now to the proper example for this. And if you can just click through just to see all of the slides, it makes it easier that way. Yep. One more. And that's it, I think. Yeah, thank you very much. So this is a nice example for you. We go back to the example we started off with, 24 volts in, 5 volts out, 2 amps, 535 kilohertz of switching frequency at 40% triple will give us a duty cycle of 0.21 approximately and an inductance value of 9.68 microhenries. That's based on these specs. We take those values and we go in and say, okay, I need to calculate my F0, my cutoff frequency. So what is my duty cycle? I already know that. My output is 5 volts. F switching is 535 kilohertz. I plug those into the equation. What's unknown? The delta VC. Now, how do we determine the delta VC? It's up to you again. Let's say you want an overall ripple of your output voltage of 50 millivolts. That's what you see in the table on the right-hand side, 0.05. That's the overall. Then you can apportion this into 2 different portions. You can say, okay, 20 millivolts can be ripple across my cap and 30 millivolts attributed to my ESR. So that 20 millivolts is what you plug in into that delta VC equation to calculate F0. So that will give you that 17.19 kilohertz, which is well below 1/10, which is great. So I've got quite a bit of attenuation at my switching frequency once that loop is closed. So having known now F0, I can substitute in the C out equation, second equation down, and now we can calculate the value of C. Next, I can calculate the value of the ESR of that capacitor that I want. So it's 8.9 microfarads. What is the ESR needed? I can just say, okay, I need 30 millivolts of delta V across the ESR. I can plug that into the equation. Everything else is known now. It's 39 milliohms worth of resistance. And finally, we can calculate the ICRMS, which is 230 milliamps of ICRMS voltage. So I have got now all of the specs to select an appropriate capacitor for my design. So I'm conscious that I am running well out of time here with all of, I guess, the interruptions that we have had. So if we just go and onto the next slide, please, I've included here a link to a tool we call Red Expert. So if you go to the next slide, the Red Expert is the tool of choice to help you with selecting your inductors as well as your capacitors. So on this slide here, I've also included a link for optimizing the selection of inductors based on the same example that we have just been talking about now. And it selects a variety of different inductors. The beautiful thing about Red Expert is it doesn't only find the value of inductance that you require, but it also, as you can see on the slide here, provides you with the losses and provides you with the temperature rise in the components, so you can optimize that selection thermally as well. And on the next slide as well, what I have done is also included a link for the capacitor side of things. Yep. So that's for the selection of the caps. And with this side of things, you can select naturally and filter based on capacitance value that you require. But you can see the extra 2 columns that we have created here, which you can look at the ESR at 535 kilohertz and the ripple current at 535 kilohertz as well. So it also gives you an indication of your selection criteria for those capacitors and how you optimize that performance. So again, that's for your information. So the final bit, maybe I can run through this a bit quicker on the spotlights for inductor side of things. Maybe a couple of things to mention on this is when we're looking at inductor side of things and inductors in particular, there is quite a wide range of options when it comes to these components, and these are primarily based on the actual material that we use, hence what gives you this relative permeability factor. and of course the type of wire that we use. These are the two key active criteria of making a power inductor. The next, of course, is the size, the dimensions of the part. That's A effective over L effective. But based on this picture, what I'd like to just point across is we do have different types or different performances of these inductors, some with a small air gap, some with a big air gap, and some that are molded. So what you can see on this picture here is quite a wide range of different architectures. And these architectures give rise to a wide different types of performance for these components. So if we go on to the next slide, please. That performance could be associated with EMI between shielded and unshielded. Naturally, the shielded inductor is much better because it's got a lot less radiated field on the outside of the component, so less likely coupling into tracks or other components or boards. If we go on to the next slide, please, Andrea, sorry.
Where the inductor
That's just showing you the measurements here again. And so next slide after this one.
Yep.
And so one of the key characteristics, of course, of selecting an inductor is the inductance value. So one of the things to point out here is to watch out for the tolerance side of things. So you have to take that into account from a worst case point of view. But the main criteria behind this is to talk about something called performance rated current, which is what we look at on the next few slides. If we have time, I think we are running out of. But I'm just going to summarize on the performance current side of things. Just a couple of points to mention with this is rated current is a measurement or a parameter in the datasheet of a power inductor that is not controlled. It's not standardized. So it's very easy, as you can see in the picture, to have a wide range of different rated currents for the exact same components, depending on connectivity of that component and how you actually test it. The test setup makes a big difference to the rated current because it's ultimately associated with the I squared RDC, basically the DC power losses in that power inductor and the heating of that inductor as a result of. And that's where maybe a few slides further down, Andreas, we can also show you what we have decided to do with from a Würth point of view is test this behavior using a standard, which is a 62024-2. It's an IEC standard that defines specifically how you actually perform the testing on an inductor, including or down to the actual PCB itself. Now, why is PCB important is what you see on this slide. The way that you get rid of heat as you power an inductor is through a PCB. And the bigger and the thicker and the wider the tracks that you connect to that inductor, the more current that you can put through it. That's the two rated current curves that you can see in red. You can put in a lot more current for the same temperature rise than in black. And the only difference is here, the type of board that you have used, either thin, small, fine tracks or thick 1 millimeter clad copper. So with this side of things, this is what brings to the need to follow a particular standard, which is what we show on the next slide, is for measuring these inductors. That's what you see now on all of our data sheets based on the IEC 22024 standard. The class of board that we have used, the size and the dimensions of that board that has been used for the testing, and the value naturally of current as the result of 40 degrees temperature rise, which is also standardized. So everything in this measurement is standardized and subject to that standard. The next slide shows you all of this, including the size of the enclosure, the way you measure the temperature, etc. So in some occasions as well, we may use a board with 40 millimeter wide copper track, 80 millimeter long copper track, and or maybe 3 ounce copper as well. Some of these boards are like this. You can see from the classification of these boards. So this might not be what you will be using. So how do we resolve this? How can we get out of this from because you're using a much smaller board, a much smaller track, a much thinner track, lower ounceage board. That's what you get on the next slide, again, with Red Expert. And if we suggest one more slide, please. Yeah. So I've included a link here for you for what we call the performance rated current custom current calculator. So on this here, you can utilize, and I've shown you just a snapshot of that tool. You can put in your own length of track, your own width of track, your own thickness of copper, 35, 1 ounce copper, 2 ounce copper, whatever you want to use. And accordingly, it will re-rate your inductor based on the size of your tracks and based again on a 40 degrees maximum temperature rise. So if the rated current or performance rated current in the datasheet says 5 amps based on a class C board, which is 3 ounce copper, and then now you enter, I'm only using 1 ounce copper and it's a much smaller track than a class C board, then okay, that current is no longer going to be 5 amps, it's going to be 3.7 amps, for example, just to give you an idea. So you can basically calculate your rated current yourself using this board. If you're happy to accept 50 degrees temperature rise instead of 40, you'll have higher rated current naturally. If you only want 20 degrees temperature rise, you'll have lower rated, custom rated current, I should say. That's you're customizing that value based on your requirements.
So let me introduce myself. My name is Jakub Jirsa. I'm application engineer focused on industrial customer in the EMEA region in terms of power products. And in today's session, I would like to show you some topic, some ideas about the active PFC solution with respect to our components and some behavior. Sorry, I start from the middle. So in this part, first I would like to show some basic of the PFC, because I don't know what is the knowledge of all the people here on the call. In the next session, we will talk about what's the differences in the topologies. Later, we will check some guidelines, how to improve the EMI behavior and so on. We will check also what component can ST offer. And we will check some topologies, some standard topologies for the PFC, and we will check our evaluation boards. So just to start from the beginning, what is the power factor and why we need it? So basically, in the power socket, we have the sinusoidal voltage, but for our inverter, for our application, we usually require DC voltage. And easiest way how we can achieve this DC voltage is to place the simple bridge rectifier to rectify the grid and to have a DC voltage. But there are some consequences of this bridge rectifier, and the main one is that you are not drawing the sinusoidal current, but you have the like peaks at the highest voltage of the sinusoidal. So the consequences of this high peak currents, there are basically two of them. The first one is that if you consider you have some distribution line of the power, you have a few socket, and if you connect this rectifier without the PFC, and you will take the peak current, you could observe the destruction of the sinusoidal in the grid. So it's the first issue. The second one is that in case you have some application taking over 1 kilowatt and you don't have the PFC, you have quite high RMS value of the input current. So in this example, it's for same power. You can see without the PFC, the RMS value is like almost 7 amps, while with the PFC, the RMS value is much lower. And of course, this RMS value is somehow linked with the power losses inside the wires in the wall, because you have some impedance, and you can see that with the PFC, the losses are less than half compared to the situation without the PFC. So just to summarize, there are a few reasons why we need the PFC. There is an economical one that you dissipate less power inside the wires. Functional, the lower currents means you don't have some false triggering of the breakers. And of course, you need to be in compliance with the standard. So you need to pass these two standards. We can identify like a different solution. I would say there is a passive PFC, which is for now quite obsolete. So that's why we will consider in this session only the active PFC solution. And most common one is the boost PFC. So what is it? So the boost converter is quite simple. You have just a rectifier, inductor, the MOSFET, and the diode. And by proper duty cycle, you try to modulate the input current to have the envelope of the sinusoidal. What does it mean? So in case you switch on the channel of the MOSFET, the inductor current is rising, and as soon as you switch off the channel, the current inside the inductor cannot be cancelled immediately. So it tries to find the way through the diode and discharge to the output capacitor. And we can observe that the input, the current is falling down. And by proper modulation, you try to modulate the sinusoidal waveform at the input of the converter. So that's all. It's the easiest topology we have, and with the different current modes, we can extend this topology for the wide range of the power. So for the lowest power, we are using a transition mode. We will comment in the next session what does it mean. With the higher power, we usually go from the soft switching to the hard switching topologies, where we use the continuous conduction mode, and we are able to achieve like few hundreds of output watt of the output power. In case we would like to take a more, usually the single stage is not enough for the single component, and we are using some kind of interleaving to get the higher power levels. These topologies are the simplest, but in case we want to achieve the higher efficiency, they are the topologies without the input bridge rectifier. So we can see two examples, and I would say the most common is the two-temple PFC, but compared to the standard bridge topologies, it's much more complex and complicated for debugging and testing. I was mentioning the transition mode and the continuous conduction mode. So let's check what is the differences. So on the left side, we can see the continuous conduction mode current. So we have the fixed frequency, and by the duty cycle, we are changing the shape of the current. While in transition mode, you can see the frequency is not fixed, but let's say the on time is somehow fixed. So it's the difference. And the advantage of continuous conduction mode is that the input current ripple is quite low. So it's better for part of the EMI. While in a transition mode, it's easier to control because this constant on time it's quite easy technique to control this part, this kind of power supply. But it's suitable only for lower powers because of high current ripple. In case we would like to compare what's let's say the requirement in terms of components for these different current modes, so we can see if we will consider a 350 watt PFC and we will work in continuous conduction mode or transition mode, you can see the RMS value will be much higher for the transition mode. But what is even more important is in terms of diode, you require quite the diode with a low reverse recovery charge. Yeah, so there is a comparison of three different diodes. The first one is the silicon carbide one, and the last two are ultra fast diodes. And there is a calculation on the conductive losses, which you can see they are similar, or even best is this one, which is the STT-H8 L06. L stands for the low voltage drop, while the R here is for a rapid. Yeah, and as you can see, there is also the reverse recovery charge, And for this version with the suffix L, you can see there is a huge amount of the power losses coming from the reverse recovery charge. So the overall losses are the best for the silicon carbide, of course, but also the ultra fast with the R suffix is really good. Yeah, the L version is not good in this option. On the other hand, if you are talking about the transition mode, the L version, we are using the same one like in continuous conduction mode. So you can see it's the lowest for the L version. So that's why we recommend the ultra fast with the L version for the transition mode PFC. Usually, you can see also the overview of our diodes. So it's always some trade-off between the reverse recovery charge and the voltage drop. Ideally, we would like to have the diode in this area, but it's not technically possible. So we can choose to have the low reverse recovery charge and higher voltage drop, or the low voltage drop but high reverse recovery charge. So these devices are for transition mode, while this area is dedicated for continuous conduction mode. In terms of MOSFET, it's almost similar. I will show you later some real measurement, what's the differences. In the fields, I usually the customer asks the question, what's the difference in EMI behavior between the transition mode and continuous conduction mode? That's why we prepared for you some real measurement to see the differences in the conducted EMI. So we prepared the board. You see the schematic is the same, but there are slight differences in components. So for continuous conduction mode, we are using a silicon carbide diode. For a transition mode, there is the ultra fast diode. And this is the measurement setup we use. So it's conducted EMI. It's quite standard setup. Always we try to keep the same position to have the relevant results. On the screen, you can see now the differences between the continuous conduction mode and transition mode. You can see that the continuous conduction mode, despite its hard switching topology, it has quite a really good result. We need to consider there is no EMI filter implemented. It's just for consider the differences inside these two control techniques. And it's also caused that the switching frequency is slightly lower compared to the transition mode. Yeah, because for transition mode, the inductor was slightly smaller. Yeah, so what I want to say is that there is no big differences in EMI spectrum of continuous conduction mode and transition mode. Both of the solution can be tuned to pass the EMI. What is more important is take care about the proper design of the PCB, and this is what I would like to show you now. So this is the board we tested in let's say non-optimized layout. Yeah, so you can see it's only single layer PCB. We have some input bridge rectifier. There is just a foil capacitor as a filter. There is no additional filter. We have the inductor and the diode, MOSFET, and the output capacitor. So in case we are charging the inductor, the current loops look like this. And in case we are discharging, the current commutates through the diode to the output capacitor and back to the input capacitor. So the current loop, mainly for the discharging, is quite large. So you can see 16 square centimeters. And this is the relevant output of the quasi-peak. Yeah. In case we try to shrink the loop, so we can remove this signal path for measurement of output voltage, and we will use the power trace a bit closer. So we can reduce by 50% the current loop. And you can see we observe some improvement, mainly above 1 megahertz or below 2 megahertz, and quite important. So in case I would like to shrink even more, I'm quite limited because of I need to keep some clearance between, there is a quite high voltage at the output. So the only option is to go to the double side PCB. So in case I put the ground below on the bottom side of the PCB, you can see there is a huge improvement in the EMI spectrum. Yeah. So now we are about 2 centimeters square. And you see, for example, this peak reduced by 14 dB. Yeah, so it's a huge improvement. So what I want to say, no matter if you are using continuous conduction mode or transition mode, but always take care about the layout, because it can do enormous improvement if it's done well. Yeah. So that's what I would like to share with you. Also, I would like to show some good practice how to lay out the PFC part. So this is the example of 1.2 kilowatt PFC, and if we go through, there is a charging loop, and always try to keep it as shrink as possible. The same is for the discharging. Also, it's good to take care about the gate loop, as Inzich mentioned before. So you can see also the gate loops are very close, or the gate driver is quite close to the MOSFET itself. And the last part, it's the control part, and it should be placed out of these loops to do not influence the currents here. Yeah, so that's also good to take care. In terms of what semiconductors to choose, I would like to share with you some measurement of the continuous conduction mode TFC we did in the past. So you can see we have some motherboard with some submodules where we tested a different MOSFET, and we tested mainly our let's say running M5 technology for hard switching, and we also tested with our dedicated technology for the soft switching. But we observed that it has also very good result in the hard switching topologies. For now, it's being replaced by M9, which is even better. But I would like to share with you this result, because you can see for the complete load range, we have the better result by almost 0.2 or 0.3%, which is quite a lot, at 85%. And also at the high input voltage, the influence of the M6 in this topology it's really high. So the efficiency is improved. In terms of diode, that is also important to choose the proper diode. So I would like to show you some measurement of the PFC at 1.2 kilowatt. The switching frequency is fixed and it's quite low, only 48 kilohertz. So maybe makes sense to consider also ultra-fast diode. So we tested ultra-fast diode and the silicon carbide one to see the differences. And here you can see the results. So they are at the groups of the efficiencies for 25% of the output power, half of the output power, and the full power. And you can see the efficiency for different kind of the diodes. In the gray and the black, you can see the silicon carbide diodes, and you can see the efficiency is the best. So there is no doubt that the silicon carbide diode gives you the best result in continuous conduction mode PFCs. But also I would like to highlight there is for example, the ultra-fast diode, which is in terms of cost more effective, and still the efficiency is quite high. So if you keep the switching frequency of the PFC quite low, like 45 kilohertz, it also makes sense to consider just ultra-fast diodes because of the cost, and still the efficiency is very high. In terms of topologies, I think we discussed at the beginning. So for today, we are quite limited with the time, so we discussed just the standard boost PFC. But as ST, we also offers some materials for the bridgeless PFC. So you can check on our website. We have quite a lot of evaluation boards with application notes. So you can check on our website.
As we are exceeding our time slots, but we have approached the end of the seminar. Just to take a quick look on the questions. So there was one question about if ST has silicon carbide based solutions for this for now or in the future. So what we have presented today was a complete system solution with this reference design for a heat pump application, which was consisting of an active PFC, an inverter section for the compressor, and another inverter section for the fan, and also some driving possibilities for valves and other actuators. That was one solution example. Of course, ST has silicon carbide products also, and we have reference designs and product evaluation boards also for silicon carbide. So, for instance, we have from active PFC, for instance, a 3-level Vienna topology PFC based on silicon carbide. This was shown in, for instance, in the reference board section of Jakub. And we have also inverter evaluation boards for silicon carbide MOSFET, discrete or based on modules. So we have separated by application. We have solutions available. Then there was a question, which MCU can be used in an automotive application for brushed motors? I have to admit, I'm not so familiar with automotive applications because I'm covering industrial applications, but we can take that question offline to answer that separately. Optimum grounding point that was addressed during the session of Jindrich. He highlighted that from the different point of views where the optimum grounding point is. The recording will be shared. Yes. The slides will be shared. Yes. Right. Okay. Well, that's a long one. Practical recommendation for choosing fully shielded, encapsulated, and molded types versus semi-shielded inductors. That's a question to Mohammed.
Yes. I've been reading through that. Yes. Thank you for the question. I guess it's from a shielding point of view. This is a couple of the things as well that maybe we didn't manage to get into, which is more on the saturation side of things that I was hoping to maybe cover in this presentation as well. So with the shielding side of thing, especially with molded inductors, which are fully shielded, not only do you limit the radiated field, which has got improvements from an EMI point of view, etc., but you also have a higher capability to achieve more inductance with an unshielded or even a semi-shielded type inductor. What you end up with, one of the weaknesses is the fact that, okay, you can handle higher currents and higher saturation levels with an unshielded or semi-shielded, because you've got a bigger air gap, and it's the air gap that stores the energy, so you're not saturating your material itself, your core material. However, with that aspect, you end up with lower inductance values. So this is, again, the juggling act between shielded, semi-shielded, and unshielded inductors. So my recommendation would always be, if you are able to go for shielded, it would be better. If you are able to go for molded, it would be better, with some reservations. So with one of the things as well that you can look at when it comes to the semi-shielded or unshielded inductors with a small air gap inductors as well, the ones I showed in the picture earlier, is the temperature effect. So as you increase the temperature, your saturation BH loop changes. And now, instead of saturating at 10 amps, for example, you're saturating at 4 amps or at 3 amps. So that means that under temperature influence, be the temperature surrounding air temperature or temperature from the board itself, heating up and getting to its steady state, that temperature is ultimately coupling or conducting onto your inductor and raising its temperature. And that changes the behavior of the actual core material. And with semi-shielded or shielded with a small air gap, what we call hard saturation type components, you end up with a massive change in ripple current. And that can be quite disastrous. From a functionality point of view, we're not talking here about just the EMI side of things. We're talking about some of the hiddens when it comes to shielded versus unshielded. With molded, you do not have that effect. You can go 20 degrees, 40 degrees, 60 degrees, 80 degrees surrounding air temperature, and your ripple stays the same. So distributed air gap, there is very little in terms of the effect on the BH loop and the saturation behavior of that inductor. So not only is it very good from an EMI point of view, but it's also good from a functionality as a storage inductor point of view as well. The question would be, why not use shear, mold it for everything? Maybe that's for another day.
Okay. Yeah. Thank you very much, Mohamed. Yeah, I think that was, I see that, well, that was the last question. No, there's, when you say heatsink to ground via CY, what does it mean that does it mean that the capacitor is not directly connected to ground? Okay. I think that was a question which, yeah, was also related to you, Mohamed. Heatsink ground via CY capacitor. Does this mean that it's not directly connected?
I think it's the heatsink, as I understood it, was not connected to a ground initially. Naturally, there would have been some kind of a thermal paste or a thermal gap filler in between. And what ended up happening was that we had a direct connection between the actual heatsink to the ground layer, which I think you've shown this as an overall setup, Hendrik, when you looked at the chassis layer versus the reference ground of the enclosure versus where the actual electronics are. So that is where those Y caps were terminated to that chassis layer, which the heatsink was not connected to. So that's what we mean by that, connecting that directly to the same ground plane. Oh, that makes sense.
Yeah, thank you. I hope this answers the question. So far, I don't see any further question here to the chat. No, okay, this is clear. Yeah, so if there's no further question from the audience, I would say thank you very much for your time here today and for your interest. As said, the slides will be shared to the participants later on, and the recording will be put to the chat here. If further questions will arise, please do not hesitate to contact us again, and we're happy to answer your questions in a direct conversation. For now, we wish you a good day, and have a good afternoon, and talk to you soon. Thanks. Bye.